In this presentation, we consider another method of analysis for AC circuits, and specifically we're going to look at the superposition principle in detail, and we'll sort of mention Y delta transformations. So you may recall in DC circuits where you had resistors connected in such a way that they were not connected in series or parallel, that across three different terminals, like A, B, and C, if you had a configuration that looked like a Y, you could convert it into a delta across those same 3 points. And often that was used to take a circuit that wasn't in series and parallel and make it so that those components were now in series and parallel. So it turns out that you could do the same thing in an AC circuit where you have impedance values. And so if you have impedance values that are not connected in series or parallel and you only have one source, you can do one of these transformations. And the equations are very similar to what we had for DC circuits with just resistors. So the main difference, of course, is that these impedance values are phasors. And so if we're going to do this transformation, we have to do the addition, subtraction, multiplication, and so on as phasor notation. So we're not going to do an example of a Y delta transformation using impedance values, but we will spend some time looking at an example of the superposition principle. So the superposition principle for AC is very similar to DC. Of course, the main difference is that we have impedance values, but we're going to follow exactly the same steps that we had for the case of resistors. And we're going to remember, of course, that Ohm's law is still satisfied, Kirchhoff's current law, Kirchhoff's voltage law, and essentially superposition principle allows us to remove all but one source and analyze the circuit as a series parallel circuit, and then take that source out and put the other source back in, or as many sources as you have, and just sort of repeat this process. And that's the idea of superposition, is your superposition, you're adding the results together from multiple sources. So the steps that we're going to follow would be to remove all the sources except a single source. And when we remove the sources, we have to do it a certain way. So we'll replace the voltage sources with shorts and the current sources with opens. So we're going to remove all but one to start with. And then after we remove all but one source, we can use series parallel techniques to determine the current and the voltage across the different components that are in that circuit. And then once we figure out those values, we can go back and remove the source that we had in there and place another source back in the circuit and repeat that for as many sources as we have. And then at the end, we'll sum the results from each of those different sources for each of the different impedance values. So here is an example picture where I have some components that are connected to both a voltage supply and a current source, and we're going to use the superposition principle to determine the voltage across this 100 ohm resistor. Now obviously we could use the superposition principle to calculate the voltage across all of the components, but that would take quite a lot of time, and the process is the same. So we're just going to focus on this one resistor for this particular example. So we start by removing the current source. So there was a current source in this space, and we basically take that current source out and we remove it and leave an open space in its place. And now we want to analyze this circuit and figure out what is the voltage across this 100 ohm resistor due to this voltage supply here. So the first thing that we realize is that this 200 ohm reactive inductor here is in parallel with the resistor, so I can add those two impedance values together as if they're in parallel. Because I only have two values in parallel, I'm going to use this special case formula for the addition of two components in parallel. So I can write the inductive component as 200 ohms with a phase angle of 90, the resistor as 100 ohms, phase angle of 0, and then of course on the bottom I would add those two values together. So I can go ahead and I can multiply the top components, and I can write the bottom components in phasor notation, and then I can divide out, and I get that the total equivalent impedance of those two components connected in parallel is 89.5 with a phase angle of 26.6. So I can redraw my picture, and I can go ahead and I can identify that the inductor at the top has some impedance value, the capacitor at the bottom has some impedance value, and now I have my total equivalent impedance for those two components in parallel that is drawn as a box here. And I've written it in both polar form and in rectangular form. So I realized from this picture that all of these components are now connected in series. My goal, of course, is to figure out the voltage across this resistor right here. Since these two components are in parallel, I essentially want to know what is the voltage across this total equivalent impedance. So I can go back and I can redraw my picture or start on a separate page, and I want to figure out what is this voltage right here. So I realize that all these components are connected in series, so I can add all those values together. The 600 ohm inductor, my total equivalent impedance, and then my capacitor. And I get some total equivalent impedance, and I can write that in polar form. And then I can redraw my picture so that I have some total equivalent impedance, which is 545.9 with a phase angle of 81.6. I have one impedance value connected to my voltage supply, so I can determine the current, which is just the voltage over the impedance. And I get that the current is 0.0183 amps with an angle of minus 81.6 degrees. Once I know the current in this circuit, I know that that's also the current that's coming out of the voltage supply here and passing through all three of these impedance components, which will allow me to figure out what the voltage is, VA, across this total equivalent impedance. So it would be the current that I found below, same current up here, times that impedance value. So here's my current times my impedance value. I can multiply them together and I get a voltage across that equivalent impedance of 1.64 with a phase angle of minus 55 degrees. So I have basically figured out what the voltage is across my resistor, which is this value here, when it's connected to the 10 volt voltage supply with the current source removed. So now I'm going to remove the voltage supply that was here and replace it by a short, and I'm going to insert the current supply back in. So here's my current supply, and I want to analyze this circuit again and figure out what is the voltage across this 100 ohm resistor. So the first thing I realize is that on the left-hand side, the 600 ohm inductor, the 100 ohm capacitor in terms of their the reactance values are in series with one another. So I can add those two values together, taking into account the fact that the inductor is positive, has a positive imaginary part, and the inductor has an imaginary, a negative imaginary part, and so I get a total equivalent impedance for those two combined together of 500 ohms. And of course I can write that in phasor notation. So basically the inductor is dominating here, right? Because I end up getting a positive value and a positive 90 degrees. So I can redraw my picture and I can replace those two components with an equivalent impedance that we found here. And when I do that, I realize that the three components that I have that are connected to the current source are all in parallel with one another. Now, even though the current source is in the center, they still are all connected at the top on one side, and on the other side of their components, they're all connected on the bottom, which means all of these components are connected in parallel. So I can now combine the 100 ohm resistor, the 200 ohm the inductor piece, and this total equivalent impedance, and I can add them in parallel. So I go ahead and I put them in their phasor notation. So I have my total equivalent impedance, I have my inductor, and then I have my resistor. I can take the reciprocal, and then I can convert those into rectangular form. And I get a total, and this gives me 1 over the total impedance, of course. And when I combine those together into polar form, I get 1 over the total impedance is 0.01221, the phase angle of minus 35. When I take the reciprocal of that, so 1 over 0.01221 is 81.9 ohms, and then of course 1 over 35, 0 minus 35 is a positive 35. So those components all connected together in parallel have a total equivalent impedance of 81.9 with an angle of 35 degrees. So that means I could take that picture that I have and I can redraw it as one current source in series with one total equivalent impedance of 81.9 with an angle of 35 degrees. So this current is passing through that impedance value, so I can figure out what the voltage is across that component. And it's just the current times the impedance. I've made sure to convert my current from milliamps into amps, so 0.2 amps, angle of 20 with the impedance, and I can multiply those together and I get that the voltage is 16.38 with an angle of 55 degrees. Of course, because these were all in parallel, that's also the voltage across the resistor due to this current supply. So now I can combine the results from the two sources to find the voltage across the 100 ohm resistor. And to combine those results, I combine the voltage VA that I found earlier across the 100 ohm resistor, and then this voltage VB, which I also found due to the current source, and I can add these two components together. In order to add them, I need to put them into their rectangular form. I can add the real parts here, and then I can add the imaginary parts, and I get the voltage in rectangular form, and then I can convert that back to polar form. So using the superposition principle, we have found that the voltage across the 100 ohm resistor is 15.9 volts with an angle of 49.4 degrees. And of course, we could have gone through this process for each of the components, but it would have taken a little more time. But the process is still the same. So you'd find the voltage or the current due to each of the sources and then add those results together.